Any questions? Okay. Pick up a little bit. Maybe you left off. All right, so we talked last time about wave goes down, reflects, comes back. And so you start to develop these harmonics. And so the simplest harmonic would be if I have two fixed heads. We were doing one fixed, one free. I forget what. I'm confused with the classes right now. We did one fixed, one free?
I think so.
Okay. So, one fixed, one free, the simplest method, basically, that's the simplest harmonic. And I believe we had the question of how many waves is this?
Cool.
All right, so if this distance here is L, L is equal to 1/4 of a wavelength. So the wavelength would be equal to 4 times L. So let's figure out what kind of prediction we would make from that. If I know how fast the wave is traveling, well, actually, let's drop back for just a second. What is the formula for speed in general? Chapter 2.
Distance over time.
All right, so I have some distance divided by time. If I have a wave here, I have something that's oscillating back and forth, and so in the case of sound, the sound is going down, bouncing back. Or I have peaks of high pressure and with low pressure. So in the time it takes to create a single wave, so that is a single wave, what is that distance called?
Wavelength.
Say it again?
Wavelength.
Yes. So the wavelength is the distance that a wave travels in the time it takes to create a wave. So that is the wavelength. The symbol is the lambda. So wavelength. And the time it takes to create a wave is called
Period.
So the period is the time, basically, per oscillation. We'll make it more generic, oscillation. But if I want to figure out how many oscillations will happen per unit time, in other words, if I flip that over, if I do oscillations per time, what is that called?
Frequency.
So we have the symbol T, capital T for period, and frequency, which is just the reciprocal of that. So 1 over the frequency is equal to the period, or 1 over the period is equal to the frequency. So this is going to vibrate up and down at 60 times a second, so it's, well, let's take a look at units here. What would be the units of period?
What is the unit of an oscillation?
Oscillation.
Seconds per oscillation.
Generally just written as seconds, but yes, seconds per oscillation. But officially, the unit of period, the SI unit for period is second. Frequency?
Hertz.
Oscillations per second would be the SI unit, which is the same as a hertz. And hertz is a capital H lowercase z. So connecting it back to what we have up here, that's wavelength time divided by the period, which is wavelength times 1 over the period, which is just the wavelength times the frequency. So for any type of repeated motion, anything that we can sort of express as a wave, we have this relationship here that the speed is equal to the wavelength times the frequency, or depending upon my mood, frequency times the wavelength. So if I am looking at sound that's bouncing off something and then coming back with an antinode at the top. So with sound, an antinode is you have the greatest oscillation in high pressure, low pressure. How would we know if we have an antinode at the top of the tube?
Antinodes, or they move a lot or they don't move a lot?
Antinode, they move a lot. How would we know when we're dealing with sound?
It's high pitch.
It's not a frequency issue.
Is it density?
You said density?
Yeah, like compression.
Not a density thing. All right, so how about a node? If the node is the point where there's no vibration of the object, like when we have in the hallway, we had the long coil and it was the point that wasn't moving in theory. If sound has no movement of particles, what would that sound like?
No.
So if I have the biggest oscillation, what would that sound like?
Something? Be loud.
I was going for, relatively speaking, it would be louder. So antinode with sound is a loud spot, a node is a silent spot. So I can bring out the tube here. Apparently, I need to plug this in. Yeah, I need an extension cord. There's one. So I can create sound here. This is 1,000 hertz. And it's incredibly loud, so let's see if we can drop that down some. Ooh, I have the stylus too, that would make it easier. That sounds just as loud. Okay. Okay. I don't want it too loud because I don't want it to drown out the other sounds. Okay. So I'm going to take that, I'm going to have it go all the way down to the bottom and back up. And so if we can make a prediction. I'm also going to plug in a temperature probe, because the speed of sound does depend upon temperature. And the formula is 331.3 meters per second times the square root of the temperature And yes, temperature, capital T, period, capital T, please don't confuse those. The temperature in Kelvin over 273.15 Kelvin. So if we know the temperature of the room, and it is 22.0 degrees Celsius. How do we know how much that is in Kelvin?
You subtract 273.15.
Just remember that you really should not go below 0 Kelvin. If I subtract two,
You add 273.15.
yes. So I got the 1559, so I got 295.15 Kelvin. I plug that into here. And what is the predicted speed of sound?
$344.38
344.38.
meters per second.
All right, so that is based upon the formula. The speed of the wave did not reset, good. I did put this. And that should be equal to the frequency times the wavelength. Well, if my frequency is, I got 1,000 in there right now, let's change it to 500. So if my frequency is 500 hertz, what should be the wavelength of the wave? Let's see if we can get that in decimal form.
0.68876.
0.68876 units.
Meters.
Yeah. It's a length. And also remember that hertz is 1/second, so when I divide by hertz, it's like multiplying by a second, and the seconds would cancel out. All right, so the wavelength is 688.76 meters, and so based upon this, I should see the first harmonic at a quarter of that. So what's a quarter of that?
0.17219
17219 units.
meters.
So when this air column is about 17 centimeters, we should be able to hear that. And it's currently really close to that. Now I can adjust the length, the amount of water in here just by moving this up and down. That the height of the water in this column should be equal to the height in this column on this side. So if I drop this down, the water level is going to drop. This is basically filling up as this falls, and eventually they'll reach an equilibrium point.
So is the symbol for wavelength, is it supposed to be like a sideways T, or is it like two things touching the ground and part of the?
Two things should be touching the ground. Putting it down over here. It's a lambda. That's the lowercase lambda, then it should be touching, I'm just having difficulty drawing here. Although one student called it a drunk T. All right, so one other thing, and I haven't quite figured out why they did this, but 0 here is 2 centimeters from the top. So I would expect us to get a harmonic. That should be the size of the air column, subtracted 2 centimeters from that, and so about the 15 centimeter mark. So somewhere around here, I would expect to have the harmonic. So 17.2, yeah, so it's about 15.2 on this scale here. So, but it's physics, so what are the chances? Don't need the temperature probe anymore. Change the frequency to 500. Can you hear that in the back? Oh. The speaker is there. I assume you heard it when it got a little bit louder there. All right. So when we were at on this, let's actually get some numbers down. I was looking at it from the other side. So it was 14.6 centimeters plus the 2 centimeters from the top that the tape actually starts. So 16.6 centimeters. That is what we got. We predicted 17.2 centimeters. So not too far off. Probably about a 5% error there. Now the next simplest pattern, oh yes, Cooper.
Is it loud at the first harmonic, because that's where the first antinote is?
That's, yes. That before then, it's gonna be sort of a mess. We don't have the constant constructive, destructive interference, which would cause the larger oscillation in pressure. So there might be constructive interference before then, but it's not at that maximum value. All right, let's figure out the next prediction. The next simplest pattern that we can get here. Well, as mentioned before, we're going to add a half a wave. So the next simplest pattern, because if I've got one fixed, one free end, this is the free end and the fixed end is down there where the water is. One fixed, one free end, well, I have to have a node at the fixed end and I have to have the antinode at the free end. How many waves is this?
3/4.
Say it again, please.
3/4.
So the wavelength, actually, we know what the wavelength is going to be. 0.68876. What will be the length of the air column? Or what is our prediction?
.5165 meters.
0.5165.
7 meters.
7 meters. All right. Currently, it is around 40 centimeters, so we need to drop that down. Let's see how much coordination I have. Speaker's there. And this apparatus does have the lovely thing of that when I drop this, it's gonna be metal scraping against metal, so, yep,
Is this the third harmonic?
this will be the third harmonic.
Okay.
Oh, there's a kink in the hose here. Right there. So it is loudest at 48 centimeters on here. Plus the 2 centimeters at the top. So this was our prediction, and what we got was so we're about a little bit about 3.2% off. Now, is this proof of what I'm telling you is true? It's evidence that supports it, but hopefully it's enough to convince you that there's some legitimacy to what I'm talking about. Questions?
Is the first harmonic, or is the third harmonic louder than the first harmonic?
Traditionally, the first harmonic is louder than the third harmonic, but that could just be my hearing. Ideally, they would be the same, but in reality, the farther it has to travel, the more that some of the energy will get absorbed by the side here. Did the third sound louder than the first to you?
A little bit.